Okay, today I hope you're getting me. Please, there's a slide I've just put in there. Are you able to see?
Yes, we can see it.
Are you able to see what is on the presentation?
Yeah, we can see it. We can see it.
Are you able to see?
Yeah, we can see it.
Okay, thank you. Now, I want us to look at some kind of reasons why we are learning about the PID control, because this is the main reason. It's almost the last bit of what you're learning, but we shall venture so much on this PID control system. And there's something here that I want us to go through the history and background of PID control, then the theory behind it. Then we shall look at some fundamental tuning things, but this one you already know. Okay, the original technology for industrial proportional, integral, and derivative PID control was pneumatic, hydraulic, or mechanical, and the controller usually had a simple interface for manual tuning. The first theoretical analysis of PID controller dates back in 1922 when the Russian-American engineer Nicholas Manovsky developed an automatic ship US Navy based on observation of the, the steersman use of current error and past error and rate of change to keep the ship on course. The controllers with the electrical system were developed after the World War II. Okay, PID control is used to control and maintain processes. It can be used to control physical variables such as temperature, pressure, flow rate, and tank level. The technique is widely used in today's manufacturing industry to achieve accurate process control under different process conditions. The PID is simply an equation that the controller uses to evaluate the control variable. The process variable, PV, temperature, for example, is measured and the feedback signal is sent to the controller. The controller then compares the feedback signal to the set point and generate an error value. The value is examined with one of the more three proportional integral and derivative methodologies. As a result, the controller issues a necessary command or alters control variable to correct the error. E. This procedure from an iterative process below is a common control loop application. So you can have the inflow, and this is a pressure uh, transmitter. The PT is a pressure transmitter, and LIC is a level indicator controller. So in this example, oil is flowing in the tank. Oil is flowing in the tank in a non-constant rate. The oil level is in the tank is the process variable. The oil level in the tank is the process variable, sorry, which is measured. And this information is fed back to the controller. So the set point is there. This feedback, the level, the valve is supposed to add, and the outflow is based on the level. So this is a level, then there's outflow. An operator enters a set point for a desired level. The controller compares the current level and with the set point and generate a value that is examined by the PID method. The controller then adjusts the valve position to correct error. So the PID controller typically use control loop feedback in industrial and control system application. The controller first computes a value of error as the difference between the measured process variable and preferred set point. It then tries to minimize the error by increasing or decreasing the control input or outputs in the process so that the process variable moves closer to the set point. This method is most useful when a mathematical model of the process or a control is too complicated or unknown for the system. To increase performance, such as by increasing the system response measures. Okay, PID parameters must be adjusted according to the specific applications. The block diagram below shows an example of a heating process that is controlled by PID controller, and this programmable logic controller, the PLC in this case. The temperature of the furnace is controlled by adjusting the gas valve. The operator set the desired temperature at the set point. The furnace temperature is measured, and this information is sent back to the controller. The feedback is compared to the set point, and an error value is calculated. So the PID equation then determines the suitable valve position to correct the error. In fact, this is an example of PID. Let me check if there's somebody who want to join the menu. Good. Now, so we were talking about this one is supposed to check on the temperature, the PLC. The PLC is an equation within the PLC. PLC is a programmable logic control process, and the heating process takes place here, so that the process is set, and the valve is a controller, and you can do the analysis with the PID system, and it will be enough for us to just see somebody's want to join. So the following figure shows a typical step response curve for after the controller responds to change the set point. The curve rises from 10 to 90 at the final steady state value within a period known as rise time. The curve rises from 0 to 63.2% of the peak value within a period known as the step response time. Then the rise time is equal to the step response time minus the dead time. So dead time is the 1%. So the rise time is almost between 10 to 90%, and the peak value is given there. Then the overshoot, then specified band for setting. Setting time is always 0.2% or 0.5%. So between this time is the step response time, and this is setting time. So the initial value. So this is just what you have discussed before. Now, when we begin with the proportional control, you know the equation. We discussed this equation. So P out is the proportional portion of the controller output, KP is the proportional gain, and E is the error set point minus the process variable. So error is given by that. So KP is a constant multiplying the error. So you know the plant is a function of error. Plant is a function of error. So error is just SP minus that. So you find that when at the beginning the error is large, at the beginning is 0 to 1 is that's an error. The point is here, but output is 0, so the error is large. But if K is 5, you can see response. It can be an overshoot. So you reduce it to 2 between, then it is manageable up to that level. So error is controlled up to here. So this is a space that does not be covered. But if you use case 5, the error is overridden and it go up above the error. And when case 1, you see the system looks like that. So let's look at the finance as an example. Assume that between 1,500 Fahrenheit and 2,000 Fahrenheit, the system response proportional such that it opens the fuel valve in proportion to the error. When the temperature is below 1,500, the valve is open 100%. When it is 2,000, the valve is closed or 0% open. The proportional band, also known as the reciprocal gain, in this case is assumed to be 500 degrees Fahrenheit. However, the proportional band is usually expressed in the percentage form. The percentage is calculated by dividing the proportional band in the engineering use of degrees Fahrenheit by the full controller range and multiplying by 100. The full controller range is, this case, is 2000 minus 70, which is 19 simple that, and the 620 is the room temperature. Therefore, the process band is percentage equal to 500 divided by that times 100, which is 25%. So the engineer can adjust the proportional band and make the system more and more responsive to the error. The rule of thumb is that a smaller a smaller the proportional band or large gain result in a large output of or a faster response to a given input error, and a larger band or a small gain result in a less response controller. However, one must be aware that an exclusively large proportional gain will lead to process instability and oscillation. So this one I know you just read, if you just want to see the integral part is just this equation here, the integral, the error is being integrated, and the area, temperature, input is used to divide so that you can get the I output. So that K is a Ki over integral of that. Normally, in the control system, they call integral as a system that is supposed to remember the past. This one is supposed to integral part is remembering the past, the memory. It keeps the memory and acts on what was there in the past. But proportional is supposed to give us the present. It controls the present system, the present response, and integral controls the past response by adding up, by getting the sum step by step and giving the comparison. So I out is integral portion of the output, control output. The TI is integral time or reset time. Then integral gain is the KI. Then error is E, set point minus process variable. Then we also have derivative. D out is the TD by this derivative of error. So the law of this TD is now TD is given as derivative time. So it is KD to that. And we get that summary. And for TD is 0.1 for this derivative part. When TD is 0.1 is an overshoot. When it is 0.7 is a decrease. And when it is 4.5, there is that kind of doesn't manage very well. But all the same, it closes the error in that manner. In practice, the most PID controller can be run in two modes, manual or automatic. In manual mode, the controller output is manipulated directly by the operator, typically by pushing button that increase or decrease the controller output. A controller may also be operate in a combination with either controllers, such as in the cascade or ratio connection, or with nonlinear elements such as multipliers and selectors. In automatic mode, the PID parameters can be adjusted during the operation. When there is change in modes and parameters, it is important to avoid switching transients. Okay, since PID controller is a dynamic system, it is necessary to make sure the state of the system is correct when switching the controller between manual and automatic mode. Dynamic means that it should be something working in the process. So you must be very, very sure that what you're doing is going to make things work without bringing complication to the system, and it can cause a big, big drawback to what's happening. The PID algorithm can also be used to control variables that may be different from the manually generated system. So I'll give you these notes, but in this below is a pseudocode of a simple software loop that implement a feedback PID algorithm. So it will have constants here, which gain is the system gain. The reset rate is reset rate. Derivative is just derivative. Variables are input development, which is process input plus derivative, input prev, process input from previous past or past used in derivative calculation. Error is different between input and set points. Set point is a set point. This is a short form. Output temperature is the value of the output in terms of temperature. Temporary output is just output of PID algorithm, so that you can develop this kind of pseudocode and run it and see what it can give you. So we said that in the tuning and the tracking, which is done, I saw it in the MATLAB, you can use it. So in the step reference, when you're using the proportional part of the PID, the transient part is increasing Kp to, let me just bring some also in. This is back on the join. Increasing Kp to a level that is greater than 0, it speeds up the response. So that this transient is speed up, the state is now increasing Kp to greater than 0 reduces, but does not eliminate any steady state offset. But transient, what about rejection and tuning and tuning of the rejection kind of thing, disturbance? So you found that transient is going to speed up response and steady state is going to reduce, but will not be eliminated. So introducing the integral action Ki greater than 0 gives a wide range of response type. Introducing integral Ki, this one eliminates offset. It eliminates offset. So this other part is not necessary. It's going to confuse you. Then D is derivative action K greater than 0 gives a wide range of response and can be used to tune the damping. So when derivative is used for damping action in the transient state, and in a steady state, the derivative action has no effect at all. So So this is the response. The example below above shows how the PID controller structure is selected to match the desired closed loop performance. This selection process can be simplified using the following PID term selection flow diagram. Sorry. Select PID term, maybe PID, at zero steady state errors on step reference. Change essential? No. Select P control. At zero steady state errors on the step response essential. If it is no, then you select the P control. Yes. Is the message feedback signal too noisy for derivative control? Yes. Select PI. So you leave the derivative. You select PI. No. Is a more damped response with a short settle time required? No. If it is no, you select PI and you select the PI and let it work. Yes, you select PID. So if no damped response is a short settle time required, then you go to PID. So PI is only selected when there is noisy, the derivative response. And if there is no steady state error required, if a zero steady state error is in a step response essential to you, no, you just go with the P. So the tuning of PID controller. So I think that the rest I just give you to read on your own because I just want you to go through that. Because this one is now going to Sigler Nichols chart. I'll send this one to you so that you're going to read it on and you'll see the importance area of this control. So just that the end part of it. This time I gave you these notes on compensator design using root locus, but then the reason why I was giving you this is just to show you the compensators. Okay, but I think I wanted to use something else. Control engineering. Okay, this one is a problem that you may have done in the card in the assignment I gave you. Yeah, an example. Let me just bring somebody in now. Okay, a PID controller is inserted in a series with a system having a transfer function. So if the plant equation is a Laplace kind of thing, I tell you that in okay the physical systems are always, when the models are nonlinear, they're nonlinear, they change with time, they vary with time, they vary with time. And control systems should be non-linear, and it should be linear, the LTI, so that should be linear transfer invariant system, so that they remain constant. Most of the parts remain constant. So you find that if you have given physical system equation, or maybe mathematical equation, maybe you have 10 this y dx x squared, like that, plus 5 y dx plus maybe 10 is equal to 20 x, like that. These are physical mathematical systems, and if they're expressed like this, they are not constant either with time. But now we change them to some mathematical variables like Laplace transform, to make them, to linearize them, to linearize them, to make them look the same. Just like you have to, if you have something that is different, this section could be different for this section. This section is different from every 1, 2, 3, 4. But to make them look the same, to make them understand each other, we use Laplace transform. So they're all going to be expressed in terms of S. So you have linearized them. You have given them a unit that is good for them, all of them. So it will be easier for you to solve mathematically by using that kind of mathematical transformation. And that is known as linearizing, to linearize, to make them be in form of one unit. You've done electrical measurement and units, and you see that conversion of units is very, very important. Otherwise, if you don't convert units, then you may not do anything much. So the PID controller is inserted in series with a system having this transfer function. Now somebody wants to design. So for you to design, for designing, for any design, to design, there must be some specifications. There must be a lay requirements. Just like in the World War II, Second World War, Hitler happened to ask the soldiers to come up with a vehicle that can work in a desert, a vehicle which can work in a desert. I know desert is very hot, and the only cooling system you can have is air. And water is not available. So that is how the designers decided to come up with the Volkswagen. The Volkswagen was and a vehicle which was developed in a desert, which can use air conditioning, air cooling only. So in any control design, we'll be given specifications. If there's any response, maybe somebody wants to get a response, maybe the steps. If this is a specified value, then this, when it is zero, the error is large. The error is large. But now you can reduce the error in a manner that up to that level. We can reduce it so fast. We can reduce it very fast, like that. Or you can reduce it until it shoots down, then it can settle down. So this is what the controllers are doing. So the system has unity feedback. Find the gain constant of PID controller required to locate the closed loop pole at this level, S at this and S at that. So you want the poles to be located in these positions of 50 negative and this one. The requirements are there, but the person who is doing this knows the reason. So we shall have, when we are driving this equation here for the PID in this Kenyatta University control unit 2, this is the PID equation. So we write it directly how it is in the PID. So this is derivative time, this is integral time, that, and that, to multiply that. We have seen it in this fundamental. We have seen it, this fundamental here. This values here. KD, TD, KTI, things like that. Now, with the negative feedback, you know very well, with the unit feedback, you'll have to get something like this, maybe. This one is something you know very well at this level. I don't even need to teach you this. We are very much advanced. So with this unity feedback, negative one here, I think it's negative one, you shall have the CS over, which is YS over RS, the Y of S over IS is equal to G of S into 1 plus G of S and R of S. No, G of S and R of S, yes. So generally, when this thing works like that, you find that we can simplify our equation based on our knowledge from control system 1 You shall have this kind of arrangement. And to remove the TI, which is a common base here, you divide everything by TI, the integral time, and you find that this one is divided and this one will just be separated from that. So characteristic equation, all of this in a closed loop system can be used to analyze the control. This base here, this denominator. For a closed loop of S, that, and that, the characteristic equation in polynomial, you multiply this S minus that, and S like that. Because it was S is equal to 50. So that is S into that, you will get this equation here. It's equal to 0. So you can equate, you can compare these values with these values here. So you find that this value here, this value here can be equated to this. Or the constant. But normally this one is easier because this one has two variables, but you cannot, but you can compare this with this, first of all. So, 2 plus 10 kp is equal to 441. Then 10 kp is equal to 441 minus 2. So 10 kp is equal to 343.9, and kp is equal to 43.9. So that is going to give you that value. Then going by that, you'll get Ti is that and Td is that. So that is the thing now. So you're saying now, as we proceed on, example that one is that. So the side poles will be based on S is equal to 2 is equal to 2 plus J. This one now you get the values for S based on what you've gotten. But in most cases, what was more important is to get the KP, the TI, and that for the design. So there's a Nicholas rules for use for selecting a PID coefficient using this kind of a formula. B over A is equal to C over D. B is equal to 1/4, 1/4. And Ziegler-Nichols proposed this method. There's also many methods here in this kind of exercise, and you can optimize the process. There's also process reaction method, whereby you get a tangent to the deflection, and you get values in that order. So you can even do all these things, you read through and get the answers up that far. It's a lot of good work here. So I gave you some notes on lecture 2 modeling transfer function, whereby you apply the physical laws, Newton laws, and you the steps of model. Okay, 5 steps of control design. You look at the requirements. You draw the functional block diagram. You look at the semantic mathematical model reduction, then analysis of the design. But for you to get a transfer function, you have to go to apply the Newton laws, like you did initially. Then you linearize the whole function. So normally this equation here is non-linear. So you, because these parameters are not known, and we would like to have a block diagram like this, and the system are maybe in cascaded, and you look at the Laplace transform and change them. Like if you have Laplace transform of this is a general equation for Laplace transform of S is as these two functions here, the real and the imaginary part. It's a complex variable, and the unit step function can also be get the Laplace of that, and the unit step function Laplace can be gotten easily as a done with this yeah, it is a over s plus a. So normally there's a table. There are two tables for Laplace transform. There's table 2.1 and 2.2. If you go to the Google to memorize this table, you must memorize this table. So you can go to Google, ask for Laplace transform table 1, 2.1, and Laplace transform table 2.2. They are there. You can download them and then go through them. They'll give you all the Laplace transforms, the simple and more complex. And normally this one, if you're given an exam, it must be attached to the exam. Or if you are not, sometimes we don't attach it, which is wrong. But if you don't attach, you have to memorize them. So general Laplace transform is given by that, and they go on and on and on. Now, the reason why I'm here is that this is an equation that you need to get linearize them by Laplace transform. You'll find that you'll end up coming down. I gave you this what to do, and you use partial fractions and so on and so forth. There's a kind of general form. This is you've done it for the transfer function for electrical network. Transfer function combining only inductor and the resistor and the capacitor. All these three elements combine everything for electrical in mechanical. If you want to analyze mechanical system, inductor, resistor, and capacitor is the end thing. So voltage input compared to voltage output, we get voltage output across the capacitor, and this linear two elements are used to give us. So these are the control elements. This is the input. This is the output part. So although the capacitor also will be an input, but the voltage will be the V of T is L, right, that. So that is that, and you'll get this kind of arrangement. And still, if these values are given, the constants are given, it will be very easy for you to see the response. You can also you put much more on this kind of arrangement, and you'll get something more complicated. So in the PID controllers use sometimes amplifiers, operation amplifiers. So this is where I was bringing you to operation amplifiers. There's one part which is supposed to be the proportional, integral, and derivative part. So the circuit for PID transfer function you shall have the three of them. So this part here is the P part. Our P. This is our I. And this is our D. So you'll be able to know which circuit is giving you the I. So normally this one is only consisting of additions of two, but it's always the proportion of this giving a negative part. So all these things summed up will be able to give you a PID controller circuit. But this one, if you have done it before, you have done all these things. So the DC motors with the gears. So this one is supposed to give you the torque. The torque. The machine, the motor is supposed to give the torque. And the motor, the machine is filled. There must be a field to excite. There's a voltage, but a field to excite so that there's a rotation to give a torque. And that torque is connected to some gears. Then there's also another rotational component connected to the damping component. Therefore, you end up having this kind of arrangement. The electrical voltage will generate that value, plus this value, plus that kind of arrangement. So torque in terms of T will also give you that kind of arrangement, which is number 2. Then the T load and the T, this arrangement here, the N1 over N2 over N1 will be the T L over Tm. The torque due to load and torque due to machine. So this is a Tm in terms of T, and TL TL to see that TL here. TM and TL T load is not indicated in the system but to the same. It's supposed to be like that. The T load and T machine is supposed to then the theta L and theta M. Yeah, theta M and theta L. One is acting in they're all acting in the same direction. TM and TL should be somewhere here. T. Okay, so the effect of the load is given that equation, and we ended up getting the equivalent circuit of the electrical energy to mechanical energy in certain kind of process, so that we can have this giving us the final answer for the same. This is an antenna control. So it's just a matter of reading and understanding. So I think if there's any question, no, there's any question, I'll respond to that question. But I think we've done enough for this morning.
Yeah, excuse me, sir.
Go ahead.
Yeah, you did mention that the derivative control it kind of maps the present, the integral, the future.
Oh
Can I
yeah,
now infer that, sorry, proportional, you said it's present, integral, future. Can I infer that derivative, no, you said integral is past. Can I now infer that derivative will be
the
mapping
future.
the future?
Yeah. So I said that there are three things. There's three things helping us to have a complete control based on the PID. Just like you put it, P is the present, integral is the past, and derivative is the future. So that's why to minimize, there are certain things that we need to minimize because you don't want to override the system based on away from the requirements, so that if you override the system away from the requirements, you generate more error. So we need to look for a system that can look at the future and see how to control based on the future, and the other one based on the past, then the present. So the P is just looking at what is there available. It follows the present, but integral follows the past, but a derivative follows the future. So all these things combined is just like we are trying to balance out everything, and that is why PID is a very, very important item or element that can bring control to a manageable level. Imagine somebody, you have a system which is not normal in human life. Human life, we just look at what is happening now. We don't know what will happen tomorrow. We can't judge it. We can't know. We can't even figure it out. Even the past we have gone, but we have a system which you can even. What we do is that we program it. We program it so that it's able to coordinate all these three and give us the most reliable output that we need. Does it answer your question?
Yes, thank you. So now there's a friend of mine from JQuad. He had a kind of robot which was trying to balance on two wheels, and it kind of swings. So he was using a PID, but he was saying he didn't tune it right because now it would fall. We try to balance on the wheels, but it would go a bit fast, fall, try swinging. So he was supposed to tune it. I
Yes.
don't know if maybe you could try and suggest to me what could be done to such kind of a system for it to be able to balance on the two on its two wheels, the self
Oh,
balance.
it was supposed to follow a track, or what was it supposed to do?
It's a robot that it's just standing on its two wheels, and then now
Oh,
it's trying to balance itself to stay upright.
oh, it's just like a human being.
Yeah, yes.
So it was falling down all the time.
Yeah, it was responding a bit fast when it's going. Let's say it's not at let's say 0 degrees. Let's say it goes at -20. It responds a bit too fast. It shoots past its zero, and then now it just fall. Uh, he said that the tuning was not right.
You know, in a PID there must be a feedback, and the feedback is always a sensor. So sensor is supposed to detect. He has to put some kind of an area where the robot is supposed to function. Then robot has to go with the sensors so that the reference, you compare the reference with what is coming output, the output of the robot, and then there's a feedback. So the addition or subtraction of the robot for this feedback, maybe the sensor, is supposed to give the robot what to do next. So it will not fall based on if you the program PLC properly, then it will never fail. The problem could have been the feedback and the sensors were not working well.
Yeah, thank you. The sensors were the gyroscope for measuring how the rotation, and also an accelerometer. So maybe I'll tell him about that. Thank you.
Yeah, normally before you develop a physical thing, you must do the simulation first. You simulate the process and see whether it is where the problem is. You can develop a virtual kind of system that is supposed to manage the robot, and the robot will, if it is working for the virtual case, then it can work on the physical case. But it needs to get some kind of assistance from those who are helping it somehow.
Yes, thank you. And I was like one last thing. I was wondering, is there a way of maybe having some form of artificial intelligence that can help determine those parameters without actually having to manually tune the system?
Yeah, yeah. So far now, the predictor, the derivative part, normally it's a machine learning technology, device. Or if you know how to do machine learning, then it will generate a code for you because it's supposed to predict what is next. And if it is programmed with the machine learning system, then it will just work. This was a part of artificial intelligence.
Thank you a lot. Thanks.
It's okay. We I'm not calling in for a cut as soon as when I'll talk to the class rep, will give me the dates that I should give you a cut. We have 2 classes per week. You can choose one, either the 1 hour or the 2 hours, where you find is more convenient. At the date that you find more convenient, I'll just roll down and give you a cut, written cut. It must be different from many things you've done here, but it is high time you do something at least for the cut. I wish you all the best as you go on with the week or the weekend. Thank you.
All right, thank you.
Hello.
Thank you. Thank you.